ordinary least squares model and show you some scatter diagrams, some regression line, where in the very first part of my lecture, we will try to interpret some regression coefficients without going into the details. So that's going to be the first thing that we will do. Take some different examples, okay, and use those examples to interpret some results. Then we'll move to the understanding of how these results are actually obtained using the method of least squares. Okay, so that's the second thing that we're going to do. The third thing that we're going to do is then unpack the least squares model using Excel. So I'll run a very brief regression in Excel. I've already run it actually. I'll share it with you and we'll see how these coefficients are actually obtained. And we'll see, so once we look at the regression results in Excel, we will see that a further understanding requires us to delve into precisely the technicalities of the ordinary least squares model. So we look at the model assumptions. Now, having done that, we're then going to move to another software, which is Stata, and you see that whether you use Excel, whether you use Stata, you get the same kind of results. So we'll then understand those results further in terms of what are the predictions, what are the residuals, okay, what it means to talk about the R squared, and of course hypothesis tests, for which we'll
I'll just
have
take
to
a second here, ma'am.
yes.
We will be having the questions side by side. You'll be answering from the chat box and Q&A, or you want to answer at the end of the session, ma'am?
Yes. So I'll combine it. So I'll just complete a topic and then I'll take some questions and then I'll move on. Yeah.
Okay, ma'am, what I request every participant is that ma'am will be taking up the questions which are there in the Q&A box. So I request
Yes.
all the participants not to put their questions in the chat box because it becomes very time consuming and tedious. So only the questions in the Q&A box will be taken. If a response is needed by ma'am, then definitely you can type it in chat box.
Yes. And I just want, right,
yes.
Sure. Yeah, please complete.
Ma'am, that is what I would just expect from the participants so that the session becomes more interactive and we are able to have more knowledge from your side or answers to the questions if they are being put up in Q&A box. Ma'am,
Okay,
anything else?
sure. No, I just have to see where is the Q&A box. Okay, so that's
it is like at the bottom, ma'am. It is the
okay.
fourth icon, if you can see, ma'am.
Fine.
Is it there?
So if I go to Zoom,
ma'am, on the Zoom
I'll check it out. I'm sure I'll find it. Okay.
Ma'am,
Yes.
otherwise I'll take it up side by side. I'll just take it up once you want the answers in half an hour. I'll just take it up. Okay.
Yeah, okay. And the other thing I just wanted to clarify is just in case I'm not able to answer all the questions today, I'm also coming back tomorrow morning. So I'll surely address
Ma'am, we'll
whatever.
try to cover the related questions, all of them.
Yeah,
I'll
yeah.
try to combine it at the
Sure.
end, which are not being answered, and we just take it up quickly. Wind up, ma'am. Thank you.
Yeah, so we stop at 1:30, right?
Yes, ma'am. So at around 1:15, I asked the participants to take up whatever questions that have not been answered by ma'am while taking her session. I'll just take it up at around 1:15, ma'am. Till then, it is over to you, ma'am.
Okay. Thank you.
Thank
Okay.
you.
So that is the plan. Okay, so we'll also be looking at hypothesis tests. So I'll take questions in just a bit. First, let me start with some examples from the two variable model. Okay, so okay, right now. To understand what OLS regression is all about, as I said, we are going to use the two variable model where the two variables are a dependent variable and an explanatory variable. Now, it is the underlying theory, it is the underlying context which determines what's going to be the dependent variable and what's going to be the independent or explanatory variable. Okay, so the examples will make that clear. Now, before I proceed any further, let me clarify that a regression model is basically what it does is to estimate a straight line relation between the two. So a regression model, when you're estimating a regression line, it's essentially estimating a straight line relation between your dependent variable and the independent variable. Now, I just wanted to stop here and talk about the equation of a straight line, which I'm sure you're all familiar with. So a straight line is of this form: y is equal to alpha plus beta 1 x, where alpha is the intercept and beta 1 is the slope. And y is our dependent variable and x is our explanatory variable. Okay. Now with that, let's just see how we interpret the slope coefficient, because in a regression, that's mostly what we want to do. Okay. So yes. Oh dear. Right. Okay. So in a straight line, as you can see on my screen, the slope is nothing but dy dx. So what is beta 1 into dx? Beta 1 into dx is simply the change in y. It's just equal to dy. It's a change in y for a small change in x. So what is beta 1 therefore? What is the slope? If you put dx equal to 1, beta 1 is equal to dy. Okay, so I want you to carry that with you as we move into our examples. So when we are estimating a regression line, the relation between two variables, a straight line relation between two variables, we are essentially estimating a line, and the slope of that line represents a change in your dependent variable for a unit change in your x variable. Let's look at some examples, and then of course we will unpack this further. Right. So what you can see on your screen on the left-hand side is some cross-section data. Now, what is a cross-section data? This is data which varies across units. So I have on the left-hand side price, which is house price, and right next to it is a variable called size. So here is house price, and here is size of the house. So I would say that my dependent variable is price. So I say that price of the house depends on size. So my dependent variable y is house price and x is its size. Now this is a cross-section variable, cross-section data set where price varies across the various observations, because I'm looking at different houses which have different sizes. So the first house is priced, so these are prices in $1,000. Okay, so the units of your variables are right here. So house price for the first observation is $300,000, and size in square meters, the first house is 2438 square meters. Let's take another one. This particular observation, which I'm now circling, the house price is $212,000 and size is 1899 square meters. Okay, so that's the data. And what I want to point out right here is whenever you're looking at any data, it is very important to look at the units in which the data is measured. So what are we going to do now? We'll see that if we use OLS regression and we estimate a straight line relation between these two, then what's going to happen is we're going to get a straight line, as you can see on your on my screen right now. So what you see are two things. First of all, there is a scatter diagram. Now, a scatter diagram is a standard way of beginning your regression analysis. You measure your dependent variable on the x-axis. So y is measured on the x-axis. Y here is house price. And the explanatory or independent variable is measured on the x-axis. So x is along the x-axis. And here you have so these little dots are nothing but a plot of the data that you see on the left-hand side. So this is a scatter. Now, when you use OLS regression, you are estimating a straight line that best fits the scatter, that best captures this relation between Y and X, between house price and size. Now, I have run this regression already, and here is your regression line. So remember what I started with, the equation of a straight line. Y is equal to alpha plus beta x. Now, as I said, I'm going to use these examples and essentially interpret the slope coefficient. So let us do that. What does this line that I have now estimated, what is it saying about the relation between house price and size? Okay, let's see that. So the line is alpha is equal to 11.2. Now that is the intercept. And beta, which is the slope, is equal to 0.14. So remember the interpretation of the slope. It is the unit change in house price for a, it is the change in house price for a unit change in size. So when size increases, so when the size of a house increases by 1 square meter, its price increases by $0.14,000. Okay, so that's 0.14 into 1,000, which is $140. Okay, so I hope this is clear. So I'll interpret a few more examples and then I'll take a question if you have any, just on this little bit that we are doing. Two variable regression, inspecting a scatter, fitting a straight line, and interpreting the results. Okay, if you have any questions on that, I'll just take it once I've gone through the next couple of examples. Okay, so over to the next example. Yeah. Okay. So now I have a different data set where, again, a cross-section data set where I'm looking at CEO salaries and return on equity for a whole bunch of firms. Okay. So again, this is a cross-section data. So the reason it's cross-section is because the underlying units are firms. For different firms, I have a dependent variable, which is Y. And I say that Y, that is how much CEOs are paid, their salaries are dependent on X, which is an indicator of firm performance. Okay, so is there any relation between how well a firm performs and how much it pays its CEO? Okay, so again, the units in which this data is measured, wages are in $1,000, ROE is in percentage. So if we yes, so once we plot the data, once you have the scatter and the line, what we get is this particular straight line. Salary is equal to 963 plus 18.5 ROE. Let us interpret the coefficient. For a percentage point increase in ROE, because ROE is measured in percentages. So when a firm ROE increases by 1 percentage point, its CEO gets paid 18.5 into $1,000. So that's 18.5 into 1,000. That's $18500. That's how much more a CEO is paid for a firm which has ROE 1 unit higher. Okay. All right. And I just have a couple more examples. Let me take you through those. Now, here, my dependent variable is wages and my explanatory variable is years of education. So again, do look at the units in which the data is measured. Okay, so wages are in dollars and education is number of years. Now, the regression line in this case is wages is equal to minus 0.09 plus 5.4 into EDU. So alpha is equal to minus 0.09 and beta is equal to 5.4. What does this say? An extra year of education increases your wages by $5.4. Okay, dy dx is equal to 5.4 in this case. Now here, do look at the scatter. The scatter here looks a bit different from the scatter that you just saw a little while earlier. Now, why is that? It's because of the kind of variable that I have as my dependent variable. So my dependent variable takes values such as 5, 10, 12, and so on. And you can clearly see that suppose I look at somebody with 10 years of education, all right? And what do I see over here? A person with 10 years of education could either be earning something like this, which is fairly low, or they could be earning something like this, which is fairly on the higher side. Okay, so it's because of the kind of x variable that we have over here that the scatter looks like this. Okay, a bit different from the earlier scatters that we saw. Right. So I think I just have one more example and then I'll take some questions if you have any. Yes. Sorry. Yeah. This, yes. Okay. Now, so far we've been looking at lines which are all upward sloping. Now here is a slightly different example where my dependent variable y is miles per gallon. Sorry, my technical glitch is playing up a bit today. Sorry about that. Just a moment. Yeah. Yes. Okay. All right. So right. So here my dependent variable is mileage, okay, for cross-section data on cars. So I have what is the miles per gallon, okay, and the weight of the car in pounds, okay. And here I have weight of the car and here I have miles per gallon. And this is my regression line. So what is this saying? It is saying that for a car which is a pound heavier, okay, its mile per gallon is actually sorry. So this should be negative. Okay, that is a glitch over here. Okay, a car which is heavier by a pound gives lower miles per gallon by 39.44 units. Okay, it's so that there's that much of a difference in terms of weight of a car and its miles per gallon. All right. Okay. So these are the examples. And as you see, in each of these, I've put a question. How did we get this slope and the intercept? That's what we are going to look at next and see how we use the OLS estimators and the OLS methodology. But I'll stop here and take a question if you have any. Okay. So I think the questions are on the Q&A box. And I just, yes, there's just only one question. Okay. What is minus alpha? Y estimate is negative. Okay. So alpha is the, I'm just using this term, alpha, for the intercept of the straight line, and beta is the slope of the straight line. So if alpha is negative, it simply means that the line is cutting the negative axis. That's all. Okay. Positive alpha simply means that the that the intercept is on the positive axis. That's all. Y estimate is negative. So if the slope estimate, if x and y are moving in the same direction, you have a positive slope. Okay, the beta coefficient is positive, and if x and y are moving in different directions, as in the car example, you'll get a negative slope. Okay, that's the reason. For a downward sloping line, dy dx is negative, which means that as x increases, y is actually decreasing. How correlation is different? So in regression, as you'll see, you'll be able actually to do a lot more than merely measure the strength of association between two variables. Okay, so especially when we move to multiple regression analysis, you will see what is the difference between correlation and regression. But as the two variable model stands, there is a very close relation between correlation and regression, because you see that the R squared from a two variable regression model is nothing but the squared correlation coefficient. Okay. So it is measuring the direction of the relation between the two, and you're also able to estimate the marginal effect. So that is one way in which regression gives you an addition over correlation. You're able to estimate the effect of the marginal effect of x on y. How much does y change for a small change in x? What is the significance of OLS? It will be clear. Why is the intercept negative? Yeah, the intercept is negative. Yeah, that's. I might have gotten a small difference in the. I just may have missed the slope and the coefficient in this one. Okay, so the intercept should have been positive, and the slope would be negative. So Boishakhi, I may have made a mistake over there. I'll come back to this regression. Okay, but it is really the slope which should be negative over here. Yeah. In the graph, yes, Dr. Mohanty, you're right. There is a mistake in the way I've written the line. All right. In fact, let me just, since this has come up, let me just run this regression once again. So it will also take care of one of the things which I wanted to do. I wanted to run a regression for you in Stata. So if you have access to Stata, you can actually run this regression with me, because the data set that I'm going to use is simply going to be a built-in data set from Stata. Okay, so let me just run this car regression once again. So if you have Stata, please open it, because I will just use Stata and I'll tell you how to access the data. Okay, so I'm glad we took the questions, and let me just move to Stata now. Okay. Now, what you can see on my screen, I hope it is visible. The Stata on my screen is visible now. Okay, so I will use a data set. Can you see Stata? I hope. Yes. Okay. So to access, can one of you just say yes if you can see the Stata on my screen? Yes. Yeah. Okay, I'll just assume that you can see it. Right. So just one moment. Yeah. So if you have open Stata, then please, yes, you can. Okay. Yeah, I will explain, Sushmita, how the intercept and slope is done. Okay. So let me just do this. All right. So if you have open Stata, this sort of a box is going to open up for you. Now, here you can see that there is a review window. This is the result window, the main window. All right. This is where variables will be listed. Okay. And this here is the command window. So how does Stata work? I will be using Stata today in an interactive mode, and it works by you typing commands in the command window, in this window, and the results will keep showing up in the result window. So I will just run this car example. I'll just run this regression using Stata. Okay. All right. So how to access the data. In your command window, type sys use auto. Okay, SYSUSE, as I am doing, sys use auto. Now, the minute you do that, you will see that Stata has loaded some automobile data. Okay. Now, to see the description of the data, just type D in your command window. Once you type D, the data gets described. Okay. So, right. So, what is the data that has been described over here? You have, as you can see, you have 74 observations on 12 variables. Now, do you want to have a look at the variables? We'll have a quick look at the variables once. How can we do that? We'll just type browse, short for BR. There. So once you have typed BR, it will open up the data for you and show it to you. So what is it that you have? You have the make of a car, you have the price of a car, you have miles per gallon, and you have several other sort of attributes of the car. A cross-section data on different cars, their prices, their weights, and various other attributes. Now, this is the data that I have used to run a regression. How do you run a regression in Stata? Very simple. In fact, what I will do before I run a regression is I will show you the scatter. So I will show you the scatter between miles per gallon, which is MPG, and weight. Okay. And I will also get the regression line. How will I do that? So look at what I'm typing. First, I will type scatter, MPG, weight. MPG is my dependent variable. Weight is my explanatory variable. I'm saying that miles per gallon that a car delivers varies with how heavy that car is. So I type scatter MPG weight, and then I put double. This is something that's just over your slash key. Okay, so you type that twice. Okay, and then you type lfit MPG weight. Okay, so lfit, yeah, right. So it'll just show me the it'll just show me the graph once I have typed this particular command. Okay, yeah, so there you are. So the command for those of you who couldn't get it is you simply type scatter MPG weight, put the two straight lines, which is just above your slash key, okay, and then type scatter MPG weight, okay, and it gives you this particular regression line. Okay, now let me see how to actually get the alpha and beta values that I just showed you. So for that, the command is simply reg. So let's type reg mpg weight. Okay. And here you can see the mistake that I have made. I'm very sorry, but the mistake that I have made in my slide is that I mixed up the intercept and the slope. So here you can see. So in the result window, if you look at the result window, you can see the commands. Okay. So the command I typed to run a regression of miles per gallon on weight is reg dependent variable MPG followed by the explanatory variable. Once I typed this, here are the regression results. So this is the full regression result that you see in Stata. Okay. Now we are going to discuss this, but right now I wanted you to interpret the coefficient, realizing that what running the regression essentially does is it is estimating a straight line that best captures the relation. So where is the slope of the straight line? So this here is the slope of the straight line. And I'll show you the scatter once again. So here is the scatter once again. Okay. So you can see this is a negatively sloping line, and that is captured in the result. So the slope is minus 0.006. Okay. And what is the intercept? This is the intercept. So the line is actually y is equal to 39.4 minus 0.006 into x, where my y here is mpg and x here is weight. Okay. All right. So now let me turn to how this is done. How is this actually estimated? And then I'll take questions again once I've done that. Okay. So now I'll explain the least squares methodology. So the very first thing that we'll do is to really look at this part of the regression output. So what have we done so far? So far, we have just learned how to interpret the regression output. This means that a car which is 1 pound heavier gives 0.006 miles per gallon less. Okay, that is what this result is saying. Having said that, how is it that we get this? Let me go back to my slideshow and then we will take this forward. So as you can see, for all the examples, the answer to this question, how did we estimate the slope and the intercept? We have used the OLS estimators. How does the OLS estimators work? Let us now see that. Okay. Yeah. Okay. Now, so as I said, let me just run through this a bit and then I'm going to take some questions. So the simple linear model can be stated in the following way. We have a dependent variable which we call y, okay, and we have an explanatory variable which I'm calling x1 over here, okay. Both y and x1 are random variables and they are observable, which means that I can pick up a random sample on y and x. They are both observable. Now, why am I picking up this random sample? Because I want to estimate the relation between y and x. Why do I want to estimate it? Because I don't know it. I cannot calculate it. Okay. So there is, for instance, a relation between wages and education, CEO salaries and return on equity, car mileage and weight. But if there is such a straight line relation, the slope and the intercept are unknown. So the slope and the intercept, alpha and beta 1, are essentially unobservable constants. They're not sitting somewhere where we can observe them. They're unobservable, which is why they have to be estimated with some data on you can observe. You can observe y, you can observe x, and you're going to use the data on y and x and actually estimate alpha and beta 1. Now, as you can see, there is this other term here which is telling you that, look, the relation between y and x is not a perfect relation. Even when I fixed x, y is actually alpha plus beta x1 plus u. What is u? U is actually at the bottom of everything. U is an unobservable random variable. It's our error term. So we will come to u, but first let us see how we used the two variable model to actually estimate alpha and beta 1. So about u, we'll come back and discuss in detail just a little later, once we've learned how to get alpha and beta. Okay. So, sorry. Yeah. So, what the OLS methodology involves is to collect a random sample of observations on the dependent and explanatory variables and fit a straight line to the scatter using the method of least squares. Now, what the method of least squares involves is you fit a straight line to the given scatter by choosing the line that best describes it, by choosing the line of best fit. Okay. And the intercept and the slope of the line of best fit are basically what are being used in the OLS methodology to estimate your alpha and to estimate your beta. How? We'll just see that in a moment. So look at the following example, okay? So here I have a dependent variable and I have an explanatory variable x. Here, y is the dependent variable is sales revenue and x is advertising expenditure. And here is a scatter. Now, when I'm fitting a line of best fit, okay, it's obvious that not all the points would actually be on the line. Some may be on the line, some would be off the line. Now, if I try to cover all the points, I will not get a straight line at all. What I'll get is something like this. So the method of least squares, involves estimating a straight line and choosing the straight line which best describes the scatter. What is the procedure for this? Well, we look at deviations. We look at the deviations of the actual data from this line, and we choose that line which minimizes the sum of squared deviations. Okay. So the intercept and slope of the line of best fit is therefore derived in the following way. So just a moment. Ouch. Yeah. Okay. So the method of least squares involves fitting a straight line of the form y is equal to a plus bx to a given scatter of observations xi, yi, as we just saw, where your choice of A and your choice of B, so your choice of the intercept and the slope is chosen in a way so that you're minimizing this particular term. What is this? This is nothing but the deviation of the actual observations from the observations on the line. Okay, so here you have the scatter, and let's say here you have your line. Okay, so if you fix any particular x, okay, this is your, okay, so suppose this is your y, okay, so you're choosing, so this line is a plus bx, okay. Let's say this is your actual data and here is your point on the line, okay. So this is your a plus bx1, okay. So you're minimizing this particular difference. You're minimizing this particular difference for each and every point, and you're adding all of them up and you're choosing the line of best fit. So the minimization procedure, okay, involves setting the slope coefficients equal to 0. So I just clear this, yeah. So you're minimizing this particular term. You're setting del z del a equal to 0. You're setting del z del b equal to 0. And here you go. These are your least squares estimators. This is how you would estimate the slope and intercept of the regression line. Carefully look at the formulae. So your intercept is y bar minus b star into x bar. And what is b star? B star is nothing but the covariance of x and y. That's in the numerator. And the variance of x is in the denominator. Xi minus x bar into yi minus y bar upon sigma xi minus x bar square. This is how the OLS estimators are obtained. Okay. And I'll just take you through an example in Excel to actually unpack all of this. So let me just run through this once more. Just one moment. Yes. So the OLS estimators of alpha and beta. So alpha and beta, mind you, are our unknown parameters. So just to take you back to the model once. So two variable regression involves estimating a straight line relation between y and x, where the form of that straight line is y is equal to alpha plus beta x. So how do you actually do that? How do you choose this alpha and beta? You use the following formulae. Okay. So the OLS estimators of alpha and beta are alpha hat and beta hat. So estimator is nothing but an equation. Okay. So it simply means that when you are calculating or when you're estimating the slope of the line, you're using this particular formula. Okay. You're using beta hat is equal to xi minus x bar into yi minus y bar upon sigma xi minus x bar square. Okay. And when you're estimating the intercept, you're using this particular formula, y bar minus beta hat into x bar. Y is a dependent variable, x is your explanatory variable. So please note these formulae down, because I'll just show you how to actually, I'll just show you that this is actually true. So what we've done so far is to see where these formulae are coming from. Where are they coming from? They're really coming from the following exercise. They're coming from this particular exercise where you are actually minimizing the sum of deviations from a straight line, and you're choosing a line of best fit, which is to say you're choosing that intercept and that and that slope, okay, which minimizes the sum of square deviations from that line of best fit of the actual observations. Now, I think this would be a bit clear, I hope, once we've looked at some examples. And let me take you to my Excel data file. And then I'll take questions. Okay, so I'll just run you through this exercise and then I'll take the questions. Okay, so look at what I have here. I have a very small data set. So this data set is kept small just for illustrative purposes. Okay, 15 observations on two variables: wage, my dependent variable, and education, years of education, my explanatory variable. Now I ran a regression of wage on education in Excel. Where is the data? So where is the regression result? The regression result is right here. Okay. So
ma'am, there are some questions relating to data and regression introduction. Can we take up those questions for a minute?
Yeah, sure. Yeah, it might help. Yes, sure.
Ma'am, there's a question by Arabita that what is alpha and alpha plus indicate?
Okay. What else? Alpha. So Aradhika, alpha is nothing but the intercept. So you have y and you have x, where y is a dependent variable on the y-axis and x is the explanatory variable on the x-axis. So the equation of the straight line relation between y and x is of the form y is equal to alpha plus beta x, where alpha is the slope and alpha is the intercept and beta is the slope. So here.
Ma'am, there's another question by Santosh and some other participants also, that why the estimate is negative, and why there's another question that why the intercept is negative.
Yeah, I've answered those questions. So I've taken a break and I think I've answered those questions. Okay. So the Q&A box questions I've answered. Huh?
Okay, ma'am, that's it. Or koi nahi tha. Rest all have been taken care of.
Yeah. Okay. So so the ones that are in the Q&A box as of now, I have already answered them. So
Thank you,
just to
ma'am.
sort of put this straight, here is your dependent variable x, and here is your here is your dependent variable y. Here is your explanatory variable x, okay, and here is, let's say, a scatter, and you're trying to fit a straight line, let's say, to the scatter, okay. The equation of the straight line is y is equal to alpha plus beta x. All right, that's what alpha and beta simply are. Okay, okay, right. So now what I'm showing you over here is the following thing. I have y as wage, which is a dependent variable, and I say it depends on the years of education. Education, which is your so this is to say that how much you are paid depends on how educated you are. Okay, and I expect a positive relation. So I expect the slope of the line between these two variables to have a positive slope. So I ran a regression in Excel, and here are the slope and the intercept. Why am I showing this? I'm showing you this just to show you how is it that these coefficients are obtained using the formula that I just discussed. So as you can see, the intercept here is -6. So alpha is equal to -6.4 and beta here is 1.02. Make a note of this, okay? So this is saying that wage is equal to -6.4 -6.45 plus 1.02 into edu. Okay, that is what this is saying, 1.02 into edu. So the slope of the line is 1.02. How are these numbers obtained? For that, I have just done a bit of OLS calculation to show you. So here you go, here. Now, remember the formulae, okay? The formulae for the formulae for this the slope coefficient is sigma y. So I'll just show you the formulae once, and then I'll take you to this. So here you go, here, right? So the OLS estimators are beta hat is equal to sigma xi minus x bar yi minus y bar upon xi minus x bar whole squared. So I have calculated this, and you can see that. All right. So first of all, here is y, here is x. Now this is your y bar. So if you can see this thing over here, all of these are highlighted. This is y bar, this is x bar. Now this here is y minus y bar. This column has x minus x bar. In this column, I have calculated yi minus y bar into x minus x bar. So if I show you the formulae, yeah. Okay. This is, as you can see, the average A2 minus A15. Okay, this is y bar. This is x bar. Sorry, this is x bar. And here I've calculated yi minus y bar. Here I've calculated x minus x bar. This is y minus y bar into x minus x bar. Here is the sum. So this gives me the numerator. And here is x minus x bar whole squared. This gives me the denominator. And here I have sigma. So this particular 100.36 is nothing but sigma yi minus y bar into xi minus x bar. And this particular term is nothing but sigma xi minus x bar whole squared. Okay, it's the sum of this particular column. And when I divide this by this, I get beta hat. And what is alpha hat? Alpha hat is nothing but y bar minus beta hat into x bar. Okay. So I'll just take you back to just show you what is it that I'm trying to do. I'm trying to show you that when you run a regression and you get some regression output, okay, when you get a slope and a coefficient, when you get an alpha hat and a beta hat, what your computer, what your package is basically doing is it is just using the line of best fit. As you can see, it is just using those formulae that we used, and it is getting the slope and the and that's how the slope and the intercept are estimated. Okay, right. So if you have any questions, okay, if you have any questions, I can take it now. Otherwise, I'll continue. So I'll just pause and just see if there are any questions. No? Okay. So I don't think there are any questions yet. So now so Sushmita had asked that please explain how the slope and the intercept are estimated. I hope, Sushmita, that your question is answered. So now I'll go on to the rest of the output that you see when you get a regression. So as you can see, as you can see that there are these standard errors, there are these t-statistics. To understand how we get all of those, we really need to delve a little deeper into the regression model, understand the assumptions underlying the model, and that is what I'll be moving to right now. Okay, right. So, yes, okay. So now alpha hat and beta hat, mind you, are the estimators. Okay, so alpha hat and beta hat are the OLS estimators. They're these two formulae. They're functions of x and y. Alpha hat is y bar minus beta hat into x bar, and beta hat is xi minus x bar into yi minus y bar upon xi minus x bar whole squared. So they're functions of x and y. What are x and y? X and y are both random variables, right? In every example that I've shown you, the dependent and the explanatory variables are nothing but random variables. And alpha hat and beta hat, being functions of random variables, are also random variables. Okay? Now, according to the Gauss-Markov theorem, alpha hat and beta hat are the best linear unbiased estimators of alpha and beta. To understand this further, we'll have to look at the assumptions of the OLS regression model, which is what I'll now turn to. So remember, our basic two-variable model. So I'll start with the basic two-variable model. So we have just seen that when you have some data and you estimate the model, what it does is it uses the least squares estimators and it gives you a slope and an intercept. And the equations that it's using for the slope and the intercept, those two equations in y and x are actually nothing but random variables themselves. And to understand where all of this is coming from, we are looking now at the model assumptions. So this is my basic model, where x and y are observable random variables, alpha and beta are simply unknown constants, and now we come to the errors. So what are the errors? The errors are unobservable random variables, which are telling you that, look, there is an inexact relation between y and x. Even when you're fixing x, y can take different values. Unlike, let's say, an equation in an exact equation in physics, okay? E is equal to mc square, something like that. So when you have your m and your c, there is an exact relation between, E is equal to mc square, all right? But in regression, that is not the case. Even when you fixed your x, okay, y can actually take different values. So the errors, which are your unobserved, okay, they are what most of our assumptions are addressing. So all the OLS assumptions are basically assumptions about these unknown errors, which are unobservable. What do we assume? We assume that the errors are zero mean and that they're uncorrelated with the x's. So basically we say that, look, in regression, you're splitting y into these two parts. A deterministic part, which depends on x, alpha plus beta 1 x1, and a purely random part u, which is unobservable. And on average, the errors are going to 0, and the errors are uncorrelated with the x's. So these two are two distinct paths. Okay, there is no correlation between the errors and the x's. Okay, there is no overlap between the deterministic part and the random part. Formally, we can write this, that given the x's, the errors have 0 mean. Now, if you put 1 and 2 together, you can see that because the errors have 0 mean, therefore there is an exact relation between the average value of y and x. So if you look at this particular thing together, I'll just take you through this. So if you look at the following thing, y is equal to alpha plus beta 1 x1 plus u. Okay, and when I take the average value of y, now because y is a random variable, so instead of average, instead of y bar, I say that it's the expected value of y. So the expected value of y given x1, I just take questions in a bit, okay? I can see there are quite a few questions. That's equal to alpha plus beta 1 x. How can I say this? Because the average value of the errors given the x is equal to 0. Okay. So therefore, right. So therefore, yeah, I'll just show you this. So this is my model saying that there is a deterministic part of x and there is a random part of x. And the random part of x on average goes to 0, so that there is a straight line relation, alpha plus beta x, between x and the average value of y. Okay. So this is what we are estimating each time that we are estimating a regression equation. And the assumptions of the regression model, as I just told you, are all about the unobserved error terms. So we assume that the error terms are homoscedastic, that they have constant variance, and that they are independently distributed. So I will just explain this in terms of a diagram, and then I'll go on to take your questions. Okay, so just give me, I think, about three or four more minutes. Okay, and I'll take your questions. So all our assumptions in the OLS model are about these random errors, which, mind you, are unobservable. That is why we have to make so many assumptions about them. We assume that they have constant variance and that they are independently and identically distributed. Okay. Alongside, we also assume that x is a variable, it is not a constant, and that the errors are normally distributed. So let me just show it to you in terms of a diagram. So just a moment. Oops. Yes, okay. Now, here is a slightly different way of putting the same thing, where I have x, which is my explanatory variable. Okay, I have x along this axis. Okay, this is my x, and here is my dependent variable y. So y values are measured along this axis. Now suppose I fix x. Okay, so remember, I'm stating my regression model as the expected value of y given x. Both x and y are random variables. So when I'm saying given x, all right, let's take a particular value of x. Let's say x1. Now, even when I've fixed x, what do I see? I see that y has a whole range of values. Okay? The whole range of values that y takes can be measured along this axis. And we are assuming that those values are actually distributed symmetrically. That's what explains the particular shape that you see over here. So this particular graph gives you the different values that y takes when you have fixed x. And what is this particular point? This particular point is nothing but the expected value of y when x takes the value x1. Okay, that is measured along here. What happens when x takes the value x2? So this is y1, this is y2. Okay, so when x takes the value x2, y takes a whole range of values like this. And the average value, okay, the average value that y takes, okay, is marked by the center of this graph. This is y2, okay? When x takes the value x2, this is the average value of y given that x takes the value x2, okay? So the regression line that you're plotting is essentially something which goes through the average values of y for the different values that x takes. So this is the regression line that you are plotting. Now, the assumption about the error terms, okay? The error terms are mean 0. So that is the first assumption. So the error terms are normally distributed. That's the second assumption. If we look at it in the following way, these assumptions are coming in over here. Just one moment. Oh, sorry, this is technical. Just a moment. Today, I'm really sorry, but the PowerPoint and this thing are just playing up a bit, and the slides are not changing as I would like them to. Yes. Okay. So the assumption about my error terms show up over here. Okay. Now this is assumption of homoscedasticity. Now where is the assumption of homoscedasticity showing up? The assumption of homoscedasticity is showing up in the fact that each of these three graphs that you have, they have the same variance. They're absolutely identical. Okay. So remember, I have the errors u, which is what is making the relation between y and x inexact. So even after I've fixed x, I get a whole range of values of y, because y is equal to alpha plus beta x plus u. But on average, okay, so on average, the errors go to 0, okay? And I have a symmetric distribution of y around its mean. The errors are normally distributed, so each of these have normal distributions, and they have the same variance. Okay, that's the assumption of homoscedasticity. And I'll just take one more minute before I come to the questions, which is to show you what happens when the errors are not homoscedastic. Because I think that's what makes the assumption of homoscedasticity a little bit clearer. So when the errors are not, sorry, okay. Yeah, right. So if you look at this particular example, Here, my X variable is years of education. My Y variable is wage. Now here I'm saying that suppose I fix years of education at 8. What do I get? I get not one value of wage, but I get a whole distribution of values of wage, which is to say that if you look at people with 8 years of education, you see that they're earning different amounts. Somebody is earning less, somebody is earning more, so that you'll get a whole range of values, and those values will have some average. That average is indicated over here. Now, carefully look at the spread. The spread of wages. So this gives you the distribution of wages for people with 8 years of education. This graph gives you the distribution of wages for people with 12 years of education. And this graph gives you the distribution of wages for people with 16 years of education. So when you do not have homoscedasticity, so when the errors are not homoscedastic, what could what could the situation be looking like? The situation would be the following. Those with 8 years of education, you see their wages don't vary much around the average. If you have 8 years of education, there are just so many things that you can do. Okay, so that some people will earn high wages, some will earn low wages, but there won't be much variation around that average. But when you look at people with 16 years of education, look at the kind of variation that you would observe. There can be a lot of variation of wages around the average. Okay, so when you are using the OLS model, you're ruling out this situation. This is the situation of heteroskedasticity. Okay, you are saying that the errors are homoskedastic. That's one of your assumptions. So what you're doing when you're running OLS when you're running an OLS regression is you are actually sorry, you are actually yes, you're actually assuming that the spread of wages around the mean is the same, no matter whether X value is low or X value is high. That is the meaning of the assumption of homoskedasticity, that the errors have the same variance. And the errors, mind you, is the random part of Y. Even after I fixed X, why does Y have a distribution? It's because there are these error terms. Okay, even after I fix the years of education, I don't get one wage, but I get different wages because different people have different reasons why they earn more or less. Okay, education is not the only thing, right? Okay, so this is what I've been able to cover so far. Let me take the questions, and then we'll just take it from there. Yeah, I think there are a lot of questions. Yes. How to get this output using Excel is what Kuljit is saying. Why do we say that error has no relation with X if U is equal to 0? Yes, Santoshi, I'll come to your question. What does 0 mean imply? How can errors have 0 mean? By assumption, that is what we are assuming. Okay. Why do we need constant variance of the error term to make OLS work? Okay. Do we need the homoscedasticity assumption to rule out any non-random reason? Okay. When you say the expected value of 0, do you mean all X or every X? Yeah. Okay. So Krishna Kumar has got the answer. Thank you. Okay. You see, Santoshi, let me start. So Kuljit, I'll come to your question on how to get this output by using Excel just after answering these questions. So Santosh, you see, we say that the error has no relationship with X. That's very important. Okay, it's very important that we say that. Let's see why. You see, we are saying that in a regression model, by assumption, Y has two parts, a deterministic part and a random part. Now, if the two get correlated, then obviously there is a problem. then the deterministic part is also random, right? Therefore, by assumption, we have to rule out. We have to rule out the fact that there is a correlation between the deterministic part and the random part. Okay, that is a very important assumption. So please note, these are all assumptions. These are all theoretical assumptions. Every time you are running the OLS model and you're taking the results seriously, you're expecting these assumptions are getting satisfied. Okay. So I hope this clarifies your answer. So you see, if I'm trying to say that I'm splitting Y into these two parts, a deterministic part and a random part, and if the two are correlated, then obviously I'm not being able to split Y into these two distinct parts, right? There's a part I know once I know X, and there is a part which is purely random, and the two are uncorrelated. That is the I hope that Santoshji, your as I said, your question has been that takes care of your question. What does zero mean imply? Okay, now you see, what it means is the following thing. Let me take the zero mean assumption. I'll just use the board. Okay, so here, oh dear, here is my X and here is my Y. Okay, now I'm saying that, look, even after I have fixed X, I don't get one value of Y, I get a whole bunch of values of Y. Now, as X is increasing, okay, so as I go on and I take some XK, let us say, then the values of Y get higher. Okay. Now, what is my assumption? My assumption is that the expected value of the errors are random. Therefore, I talk about expected value of errors and not average, is equal to 0. What does that mean? It means that after I fixed X, okay, so this given X means I fixed X, okay. So when I fixed X, I get a whole bunch of values of Y, right? There are about as many positive as there are negative deviations around the average. That's what it means to say that the expected value of the errors is 0. Okay. So even when I fixed X over here, I get a whole bunch of values of Y. There are about as many positive so there are about as many positive values around the average as there are negative values. So here, let's say, here is the line. Okay, sorry. So this should be a straight line. Okay. So what is this line? This line is the average value of Y given X. This is equal to alpha plus beta X. Okay. So I say that because the expected value of U given X is equal to 0, okay, what that means is around the average, there are about as many positive deviations as there are negative deviations. That's what explains the symmetric shape of the graph. So if I take you now to that graph and answer the question once again, here, sorry, just one moment. So yes, so you see, this graph is perfectly symmetric around the mean. That's what it means to say that the errors have zero mean. Even when you fixed the X, there are about as much upward deviation over the value of Y as there are negative deviations. So to take it in the following way, for wage and education, for instance, all of these are symmetric. They have different variances, but they are all symmetric. I'm saying that if you look at people with 8 years of education, there are about as many people who earn more than average, whatever is the average earnings of people with 8 years of education. There are about as many people who earn more than the average as there are below, as earn less than the average. I hope this answers your question. Okay, so that was Priyank's question. Now, Baisakhi, why do you need constant variance? You see, this is very important to prove your Gauss-Markov theorem. Now, the Gauss-Markov theorem is a theorem which tells you that the OLS estimators are blue. Now, the blue property of the OLS estimators depends on the assumption of constant variance. If the variances are not constant, we say there is heteroscedasticity. It means that the OLS estimators will not be blue. Okay, so to prove that result, we need the assumption, which is why, we always check whether this assumption is getting violated or not. Because if it is getting violated, then there are fixes. Do we need this homoscale to rule out any non-random? Ouch. Baisakhi, that's a very complicated question. I'm not even going to let me not go down that road. I hope I've clarified why you need that assumption of constant variance. Okay, to prove your OLS regression, to prove the blue property. Okay, so are there any more questions?
No, ma'am, you have answered all the questions.
Okay, so
I
have
anyone
yes. So I have I think 4 or 5 more minutes.
Ma'am, yes, and basically a lot of questions are being asked on Excel and all that. So I
Acha,
think
yeah, so let me show you. Yeah, I'll just ask you. I'll just show Excel. Okay.
and
Yeah.
there's a question by Professor Rajendra sir also, that how to draw a scatter in Excel. I think this answer question was taken up yesterday also. Ma'am, if
Yeah,
you
I'll just show it and it will come. Okay. I'll just show Excel and then I'll just go to Stata.
okay,
Bus.
thank you, ma'am.
Okay. Yeah. Yeah. Okay. So how many minutes, Anjali?
And we
Another
have
5
around
minutes.
10 minutes, ma'am.
10 minutes. Okay. Okay. Fine. All right. So here you see I'm to run this regression in Excel. What you need to do is hang on, I'm just trying to get rid of this. Okay. Yeah, it's gone. So you need to have this data analysis tool. Okay, this is what you need. You need this. Now, how do you get this? In case your Excel is not showing it, then you go to File. Okay. Sorry. So you go to File, and then you go to Options. Okay. So once you open File, it'll give you a whole bunch of things, and you go to Options. And in Options, you will see there's this thing called add-ins. Okay. Now, in your add-ins, add in the analysis tool pack. Okay. Just add in the analysis tool pack, and you will be able to. So you just have to say go. Okay. So here you'll have to do this thing. You say go and okay, and it's going to add this analysis tool pack for you. Okay. That is what I have done. Now, once I did that, what happened is the following thing. Yeah. Once I did that, it gave me this data analysis option. Now, how do you run a regression in Excel? You click on data analysis. Okay. Once you've clicked on data analysis, it will open all these things and you will see regression. I hope you can see it'll show regression. And once it shows that, you go okay. Okay. So regression, yeah, and it's going to open this dialog box. Now, once you have opened this dialog box, I'll just show you. You will be asked for the dependent variable range. Specify that. Explanatory variable range. You specify that. Ask for data labels. Okay. This is a default confidence interval. You can ask for some other confidence interval also. The output will be shown in a new worksheet. Ask for residuals, ask for residual plots, and here's your scatter. You can ask for your line fit plot also. So once you've done this, once you do okay for all of this, okay, then it's going to give you the results. All right. And the results that it's going to give you will look exactly like this. So the results that's going to give you will look like this. Sorry, cancel. Yeah, I've already done all this and here you are. All right. So here are the coefficients. Here is your alpha hat and beta hat, and I've been talking about that. Here is your R squared. Okay. And here are the analysis of variance tables and so on. Since I'll be talking about this tomorrow, I'll take these up tomorrow. I just want to show you something else over here, which is here. which is the predicted values. Okay. So here are the predicted values and here are your residuals. So very quickly, what are these? Okay. Now I have run a regression of wage on education, and this is my regression line. So the predicted values are all the points on the line. Okay. So if I were to just copy it over here, in the next sheet, right? So you can see here is my beta hat, here is my alpha hat. So what are the predicted values? The predicted values are, they are also called y hat. Okay, so what is this y hat? It is nothing but, so it's equal to alpha hat. Okay, so I'm going to just alpha hat plus beta hat into x. Okay, here. So do you see? So the predicted value is nothing but the point on the regression line. Okay. Where is the regression line? So you can see the regression line is over here. I have asked for this output and here is the regression line. Okay, line fit plot. Yeah. Okay. So here the predicted wages are given by these yellow lines. So this particular regression line. So I'll just end with this. I think the time is almost up. So what I want to show you is the following thing, that along with your regression output, you get your y hat. All right. And as we just saw how to calculate y hat. Y hat is a point on the regression line. Okay. So this is your actual y. This is 3.1. So okay. Just look at this. So this is my data. I have data on wage and I have data on education. This is the first observation. This is the first person who has 11 years of education and who earns $3.1. Okay. So this is my Y. Now, once I have run the regression, what have I got? I have got the straight line. The straight line is of this form. Minus 6.45, which is alpha hat, plus 1.02 into education. Okay. Beta hat is 1.02. I get predicted values. What are these predicted values? They are points on the line. They're points on your regression line. So it's simply alpha hat plus beta hat into x. I'll do it once again. So this is equal to alpha hat plus beta hat into x. Now what is x over here? 12. This is for the second person. There you go. Okay. So the first person is actually earning $3.1, but your model is predicting that somebody with 11 years of education should be earning $4.8. The second person with 12 years of education is actually earning $3.24, but your model is predicting that this person should be earning $5.8. Okay, so that's the difference between Y and Y hat. And along with this, we have the least squares residuals. What are the residuals? The residuals are actually your, so we'll call them U hat. So remember the U's? The U's were unobservable. The residuals are actually giving you an estimates of your U's. Okay. So this is equal to Y minus Y hat. The actual observation, 3.1, minus the predicted. Okay. So again, same thing. This is equal to actual observation minus the predicted. Okay. There you go. So I think this is what this is like a very important part of your regression results. And I just wanted to show you how this works out. Okay. And what it actually is. So along with your predicted values, you're getting the least squares residuals. And what are these residuals? These residuals give you an estimate of your unobserved errors. So the errors were unobservable, they were unobserved, but once you have the data on X and Y, and you run a regression model, you get an estimate of the errors. So as you can see, I have negative residuals. The first two residuals are negative because in this case, my y is less than y hat. So what is my u hat? My u hat is nothing but it is y minus y hat. The point on the line, so the actual point minus the point on the line. So just to sort of show you what it is, here you go. So here you have y, here you have x, okay? Here you have the scatter, and let's say here you have a straight line. So once you have x, okay? So this is your y hat, okay? And this, which is the actual observation, on this is the scatter, this is your y. So this is your y, so that this little thing is your error, okay, is your residual u hat. U hat is equal to y minus y hat. Okay, so whenever we have someone actually earning less than what's predicted by my model, I'll have a negative residual. And look at the positive residuals. So let's look at this, for instance. Okay, this is my 10th observation. Now here, a person with 17 years of education is earning 18, is actually earning $18. And my model predicts that he should actually be earning $10. So he's actually earning a lot more. So y minus y hat in this case is positive. Now, just by the least squares methodology, the least squares methodology actually minimizes the sum of squared residuals. Remember, the least squares methodology is minimizing the sum of squared deviations from your line of best fit. So what it ends up doing is it's actually minimizing the sum of squared deviations, right? And when you're minimizing a squared, when you're minimizing a sum of squares, it can't possibly, the minimum can't possibly be negative. It's being driven down to, to zero, right? And the average value of the least squares residuals is actually zero. That's part of the least squares methodology. Okay, so the least squares residuals, if you look at the average of this particular column, it'll go to zero. Right? So I think perhaps the time is up. I'll just show you the, yeah. So if you look at the average of this whole column, this will go to zero. Okay, now see this number, it says E minus 1.5. That means this is, divided by 10 to the power 15. It's 1.2688 divided by 10 to the power 15. So there are it's practically zero. Okay, this is this is just to show you that by the method of least squares, when you're fitting a straight line, it's minimizing the sum of squared deviations. It's actually the sum of squared residuals, and the average residuals are driven to zero by your least squares methodology. Anjali, do I have any time left, or should I end now? Are there more questions? Okay.
On the questions, we don't have much question. I'll just repeat. All the questions have been answered, ma'am. Even the Excel questions are being answered. I'm not having any questions in the Q&A box, and no questions even in the no, ma'am, no questions.
Okay, so yeah, can I just take 2-3 more minutes to just point out a couple of more? Yeah,
ma'am, yes, definitely, ma'am, definitely.
Okay, fine.
I'm down here only, ma'am. You can.
Okay, fine. So I'll just with the, there were some questions on the residuals. I hope the questions on the residuals have also been answered. I just
Yes,
want
ma'am.
to point out, another feature of the output. Okay. I'll just use this Excel sheet because this is what we've been discussing. But the same results you will also get also in Stata. Okay. Now see, what is my least squares regression really doing? You're trying to explain the actual variance in wages through the variance in education in this model. In this model, where I have regressed wages on education, my dependent variable is wage and my explanatory variable is education. I'm trying to say that, look, there is a certain amount of, there is this certain amount of variation in wages. Different people are earning different wages. And I'm saying that's because different people have different levels of education. That is what I'm trying to do. Okay. Ask to what extent the variation in wages is explained by variation in education, years of education. Now, where is this showing up in your in your results? Now, look here. Look at this particular part of your results, which says ANOVA. Now, ANOVA, I know you have already done ANOVA. So it's analysis of variance. And where is the variance showing up? It's showing up here, SS. So SS is sum of squares. Okay. So when you're looking at variance, it's sigma xi minus x bar whole square. So it's you call it the sum of squares. Now, I just want to end by pointing out what is going on. Look at the ANOVA table. There is a total variation. What is this total variation? This is the total variation in your dependent variable. Okay. This is a variance of wages. Now here is your regression variation. What is this the variation of? This is what you have explained through your model. So you have, what are you trying to explain? You're trying to explain the variation of y. Now, what is your regression model giving you? Your regression model is giving you y hat. What is y hat? Y hat is equal to alpha hat plus beta hat into x. Okay, so this is your predicted values. So this 102.77, this is the variance in your y hat. This is the variance in your predicted wages. So how much have you explained? The total variation is 217. And how much have you explained? It is 102. So what is left? You haven't explained the rest. This is your residual variance. Okay. So what you're trying to do through your regression model is use education to explain variance of wages, and the extent to which you have been successful is captured over here. Okay, this is your R squared. So the R squared is nothing but a measure of what percentage of the total variation has been explained by your model. What percentage of the variation in y is explained by the variation is explained by your model? That is, it is a ratio of the variance of y hat to the variance of y. Okay, so you can take any data set and you can check that if you divide this 102 by this 217 thing, you're going to get the R squared. Okay. This is one verdict on your model. This is one verdict telling you how you have done. Now, apart from that, so what we will discuss tomorrow in context of the multiple regression model, because my plan is to really talk about different kinds of functional forms, to do hypothesis tests and so on, which we will be taking up tomorrow. Is going to we're going to see that in a multiple regression model, we don't just look at the R squared, we also look at the adjusted R squared. And there is one other thing which is coming over here, which is your multiple R. This multiple R is nothing but the correlation between your y and your y hat. Okay, so these are some of the things that you can actually check. So all of these are giving you different verdicts on your model in terms of how you have done, how much of your variation, how much of the variation in the dependent variable have you been able to explain through your regression model. That's really what all of this is telling you, in particular your R squared. Okay, right. So I think perhaps I've not been able to cover as much as I wanted to today, but I do hope that we've made a beginning, and I'll look at the remaining issues when we start tomorrow. So we'll look at the standard errors and the standard error of your regression, what it means, and the hypothesis tests, and interpret coefficients. Interpret the coefficients from models with different kinds of functional forms. Okay. Yeah. So, are there any more questions?
No, ma'am, there are no more questions. It's rather that I have got compliments, ma'am.
Sorry.
I don't mind reading a few. Ma'am, in the other way, a lot of compliments are coming your way. That by
Okay.
Sultan Singh sir, that thank you, ma'am, for words of wisdom and a nice session on regression analysis. It is a very. I'm getting one of the participant is saying that, ma'am, you have explained very nicely,
Okay.
and definitely even it is simple to understand for those who are not having any statistical background. So
Okay.
thank you, ma'am, for all these this.
Not at all. If there are any questions, I mean, yeah, I mean, I can take any questions.
No,
Otherwise,
ma'am, there are no questions. Like all
Okay,
have
okay.
been answered, and I request the participants that tomorrow again we'll be having Ananya ma'am only on regression. So any aspect of the regression that is any participant is having any confusion, the same can be taken up once in 5 minutes in the morning before ma'am proceeds with her next topic for the day.
Yeah. So if they share some questions, they can, yeah, certainly. So, I'll definitely do that. If you have any basic questions, I'll just start with that. So tomorrow, we will start with the multiple regression model and look at interpretation, functional forms, hypothesis testing. Hmm.
Definitely, ma'am. Thank you, ma'am. I just thank you for the session on behalf
Not at
of
all.
Ramanujan, TLC Center, Ramanujan College, and on behalf of Indian Accounting Association NCR chapter, and
Thank
my
you.
on my own behalf for always accepting our invite to be a part of the endeavors that we take up from time to time. Thank you, ma'am. Looking forward for the session tomorrow also.
Thank you.
A very
Okay.
good afternoon to all. And with this, we conclude this session today. Thank you, ma'am.
Okay. Thank you. Thank you.